Now we want to talk about a variation of Lovász's two families theorem due to Freddy. So here's the theorem by Freddy in 1984. So we again have subspaces, pairs of subspaces. So V1 up to UM and V1 up to VM be subspaces of a vector space W over a field F. And we still have the same condition. So dimension of UI is R, dimension of VI is S. Now there's a difference. So the difference is, so previously we assumed that UI intersection VI has dimension 0. Now we assume that UI intersection VI has dimension m most t for all I. And UI intersection Vj has dimension bigger than t for all I less than j. Then number of pairs is at most something. I think we have to assume that yeah, I mean, we don't have to assume that R or S is bigger than T, because second condition already implies that R is bigger than T and S is bigger than T. All right, so that's the theorem. And how are we going to prove it? And we use the argument about the subspace in general positions. So we may assume that the field is big. The bound will be, I mean, so just by taking an extension field, I can assume the field is as big as I want, and it doesn't change the problem, right? Because the bound that we are obtaining is independent of the size of the field, right? The bound m, the upper bound m, r plus s minus 2t choose r minus t. This is independent of the size of field. All right. So by previous theorem on the existence of subspaces in general position, there exists a subspace. Okay, so let's say n is a dimension of W. V of W of dimension m minus t, which is in general position with okay, let's list all of them: UI, VI, UI plus UI intersection VI, and UI intersection VJ. I mean, okay, just I can say UI intersection VJ for all I less than or equal to j. All right, and number of these list of subspaces is finite. Therefore, there exists a subspace V in general position without all these things. Then dimension of UI intersection V is dimension of UI minus T. Dimension of VI intersection V is dimension of VI minus T. So this is R minus T, this is S minus T. Dimension of UI VI intersection V. What is that? This is the dimension of UI intersection VI intersection V, which is which is a minimum of dimension of ui intersection vi minus t and 0, right? And that's 0, right? So this will be 0. And dimension of ui intersection v intersection vi intersection v is dimension of ui, again by the same argument. Right? So now if you take ui prime be ui intersection v, vi prime be vi intersection v, then apply Lovász's theorem. Right? So where is it? We apply that theorem. This implies that m is at most r plus t r plus s minus 2t. Choose r minus t. All right. So that's the proof. Now here's a corollary. So here, let's say you have a set A1 up to AM and B1 up to BM. B subsets, okay, whatever. Let's say integers, such that AI intersection BI has size B less than size at most T for all I, and AI intersection BJ has size bigger than T for all I less than J. Then number of such a family, size of such a family. Okay, also I assume that AI has size R, BI has size S. Then we get this bound. Right? Why? Right, I mean, instead of set G, let's just, it doesn't matter, right? You can just take a n to be big enough. The proof is just map I to the EI, right? Right, so if you have a number 1 that maps to 1 0 0 0, number 2 is mapped to 0 1 0 0 0, right? And then you can map each AI to be a subspace UI of the R to the N, and BI as a subspace VI of R to the N. And then in the section of AI and BI, the dimension of that, I mean, then AI intersection BI is equal to dimension of UI intersection VI. And intersection of BJ, same as dimension of UI intersection BJ, right? We are mapping the elements of finite set into the elements of the bases, so that intersection, the dimension of the intersection is exactly equal to the cardinality. All right, so that's the proof. And as far as I know, this is the only proof of this fact. Right? There's no other proof known except this method. So it'd be interesting how you could prove it without using linear algebra. All right, so that's it.